All right, I think we got that going. Okay, go ahead, John, if you want to start the intro.
Hi, everybody. Tonight's speaker is Dr. David Szabo at NASA Goddard Center. He's the chief of the Heliospheric Physics Lab. He is project scientist for the NASA Wind spacecraft orbiting in the Sun-Earth L1 location and mission scientist for the Parker Solar Probe mission. Welcome, Dr. Szabo.
Thank you very much for the gracious invitation. So I am the NASA mission scientist for the Parker Solar Probe. Parker Solar Probe is one of the latest NASA flagship missions. That means that it's sort of $1 billion class mission. Not quite James Webb class, but we are nevertheless very proud of this mission. Tonight, I'm going to take you for an exploration of the near-Sun solar wind using this great mission called Parker Solar Probe. We will start our journey with a nice sunset. Not much different that we could see probably outside the door today. The sun looks very peaceful, very romantic, and sort of very smooth and featureless. For solar physicists, the sun looks very, very different. So here is a close-up view as generated by the Solar Dynamics Observatory, yet another big NASA mission that takes pictures at various very narrow wavelengths associated with higher temperatures. So this is not a white light image. This is an extreme ultraviolet narrowband image. In this, what you can see that the sun is very violent. It's constantly churning, constantly boiling. Things keep exploding and expanding and changing. The sun's surface is really hot, of course, that's not a big surprise, but it's so hot that the hydrogen atoms, the electrons are stripped away from. So we have the state of matter that in high school we call plasma. That means that all the particles are charged. And once you strip away an electron from a hydrogen atom, of course, you end up with just a proton. So we have a whole bunch of protons and electrons floating around. About 4% stripped helium nuclei, which we call alpha particles, and then traces of heavier elements, again, without their outer shell electrons, things like carbon, nitrogen, oxygen, all the way up to iron, but in smaller quantities. Now, as you can see that we can see loops which represent magnetic field lines. It's not that all of a sudden we can see magnetic fields. What we see is that the hot plasma from the sun is trying to escape, and since it's charged, it feels the magnetic forces, so it gyrates around the magnetic field lines, and it has to follow the field lines. So think of it like cars following the highways. The protons and the electrons have no choice, but they have to follow the magnetic field lines. And as they stream away from the sun, they find that the highway has a U-turn, so they have to turn around. And so if you look at the loops, the particles come up, and the loops, then they go right back down. So what we see here is the hot particles emitting light, and of course they trace out the highway system, the magnetic field lines. Most of the particles, the upper atmosphere of the sun, thus cannot escape. They are confined to the sun. Doesn't matter that they are very hot and they are ready to escape, they cannot do so. There are only very special spots on the sun that is open. The magnetic field lines are open, and so that the plasma can escape. This image, again, is taken from the Solar Dynamic Observatory. We moved to now 1 million Kelvin so that we can see a different aspect of the sun. And what you see here, what appear to be holes at the poles, and then here it's an unusual time period. We also see a so-called corona hole at lower latitude. It's not that there is a hole in the sun. this is again taking a picture at a very specific temperature. It just simply means that there is no plasma at that particular temperature at that particular location. That is, the plasma here is colder than the hotter plasma around there, which is not a terribly big surprise because the field lines tend to open up, the plasma stream out into interplanetary space, hence it becomes colder than the trapped particles elsewhere. These escaping particles form what we call the solar wind. That's the escaping upper atmosphere of the sun, then keeps on streaming away from the sun all the way past Pluto and Neptune, reaching to the order of 140 AUs, where the Voyager spacecraft have been tracing it. By the way, the Voyagers now are truly in interstellar space. They reach the end of the influence of the sun, but it is many, many times further away than the outermost planets. So we have a big underlying question when it comes to this escaping solar wind. When the solar wind starts its life and it starts evaporating, it leaves the sun at a leisurely 10 to 100 kilometers per second. And no, I didn't make a mistake. It's not kilometers per hour, it's kilometers per second. Just to give you a sense that the speed here, the fastest bullets don't quite make it to 1 kilometers per second. The fastest man-made rocket can get up to 10. The Earth orbiting around the sun goes around 30. So it's only for us, when I say that 10 to 100 kilometers per second, it's a leisurely speed for the solar wind, because that's how it starts its life. But when it leaves the sun and it travels about 1 or 2 solar radii, reaches the corona, which is the outer region of the solar atmosphere, suddenly it undergoes a major acceleration and reaches speeds of 300 to 800 kilometers per second. So tremendously high speeds, which we do not have a good understanding how this happens. So that takes us the first big question that Parker Solar Probe is attempting to answer. Why does the solar wind speed up? And it's critically determines its characteristics as it flows away from the sun, and I will come back to that. Why does this acceleration takes place at a certain point? Now, it's not that we are completely devoid of ideas. In fact, I will return to this, that when you have an unanswered question in science, how you can tell in the broad public that scientists don't know the answer is not that they will tell you that we have not the vaguest what's going on. Instead, what you will get is from 5 scientists, you will get 10 different answers, all purporting to answer the question. That's a clear sign that we don't know what's going on. When we will converge to a single answer, then that might actually be right. It's still no guarantee, but it might actually be right at that point. 10 different answers, they all cannot be right. Possibly some mixture of the ideas, but they all cannot be right. So this is our first question. How does the solar wind accelerate? And we have multiple ideas, hence we do not understand how it happens. Now, I have to take you through a map of different temperatures of the sun to illustrate our next big conundrum. If you look at, and hopefully you can see my laser pointer, big red dot, if you look at the sun with a pinhole camera, and don't look at it with your eyes directly, you will see sunspots. So this is in just white light continuum, a typical image of the sun. If we devise instruments that actually are very narrow in wavelengths, we can focus on particular transition lines of various elements. So for example, iron has certain transition lines that only happen at a very specific temperature, so that only iron particles, or in this case ions, that have a certain temperature will emit that particular wavelength. So if we filter our observation at that particular wavelength, we can take a picture of the sun at that particular temperature. So if we look at sort of here is 4,500, 6,000 Kelvin, which is not too hot for the sun. That's sort of the photospheric temperature. That's the visible surface of the sun. When you see the sunset, this is the ball of fire that you see. Now, again, there's nothing solid there. The sun is a big boiling gas, so there is really no big difference between this surface a little bit below or a little bit above. The only reason we see this as a solid surface that at this point, photons cease to collide with each other. Photons start all the way from inside the sun, but as they collide, what our eyes interpret as an image is the point of last collision of that photon. So this is what we see here is where the last time the photons interacted with each other and collisionally they came all at 1 AU, 1 astronomical unit, to our eyes. So as we increase our temperatures of our filters, notice that these black spots, the sunspots, sort of fade away, and instead we start to see bright activity. The dark spots are intense magnetic fields that tends to cool a little bit the sun, so that's why they appeared. They are actually, if you would magnify it out, it's actually really, really bright, except the surrounding is much, much brighter. So it's only relatively speaking, they are dark spots. When we get to higher temperatures, we start to see that actually there's lots of activity going on above these sunspots. But what I want to draw your attention to, that as we start to climb in temperature, sort of get to 1 million and 2 million Kelvin, notice that the sun became hairy, fuzzy. It's because all of the sudden material next to the sun in a higher atmosphere becomes visible. At the colder temperature, it's not that we cut off the picture. There is the same amount of plasma for all the images, but we don't see any material here. So one of the curious things is that as you climb up to 1 to 2 million degrees, which is significantly hotter than the photosphere, we start to see material in the corona. Then you go even higher temperatures to 10 million, and now you can see is the explosive activity of the sun, the truly high energy events. And so again, the fuzz diminishes. So this is a big enigma in solar physics, that why is it that the surface of the sun is 4,500 to 6,000 degrees, and as the solar wind starts to stream away and expands, because it's a spherical expansion, it's from a ball and it fills all space. And from thermodynamics, you might remember that if you expand the gas, it's supposed to cool. Well, here, instead of cooling, all of a sudden the temperature skyrockets. That makes no sense. Something has to feed it. So again, we have multiple ideas, the wave electromagnetic waves get into resonance with particles, magnetic reconnection. Again, a whole slew of ideas indicating that we really do not understand why is there this tremendous heating. Now, the two questions, how does the solar wind accelerate and why is it so hot in the corona? They're probably related. That there is an energy source, and that energy source kicks some particles, it gives them kinetic energy, and some other particles, well, they just heat them up. Both requires an energy source. So those are the first two questions, and I will give you one more, just so that you know there is an end. So let me start with this kind of image. This is called a coronagraph. Normally, it's very hard to see close to the sun because, well, it's very bright. And so next to it, everything looks dark. So how do you take pictures of the solar wind next to the sun? We can do that during solar eclipses when the moon conveniently blocks out the light. And then so we can see the less intense light around it, the corona. Or in space, we can just put an artificial block in front of our camera, and then all of a sudden we can expose our camera to these are many minute long exposures so that we can see dimmer things. And all of a sudden we start to see structure. This light is again just pure white light. It's not filtered. This is a reflected or deflected light by electrons. So the light starts out from the sun, runs into the solar wind electrons, and makes a turn, and that's what ends up in our camera. But it conveniently maps out the flow of the solar wind. So we see that they are higher density streams emanating from the sun. Now I will turn on next, hopefully. I know that. I think I have to turn off the, hold on, the laser pointer. Here we go. So you can see that there are structures coming out. And I want to draw your attention that when there is a ball of transient coming out, soon after we have this snowstorm. Now, it's not that we had inclement weather in space all of a sudden. These are energetic particles that reached our detectors. And so each energetic particle sort of turns on for a little while that particular pixel registering as light. Now, these are lower energy particles, but they are also at the same time much higher energy particles also are kicked out by the sun. These are 10 to 100 million electron volt is the unit we use. These particles travel near the speed of light. There are very few of them, but they are extremely dangerous, particularly for technology. So when they hit electronics, it's not that they blow up anything. They can rewrite the code. They can flip zeros into ones and vice versa. They can cause latch-ups, the little electronic switches in the circuit boards. So all of a sudden, it makes the satellite do unplanned things, which could, some of these flips of bits can be completely negligible, at other times rather dangerous. They're also dangerous for astronauts. Now, luckily, the Earth's magnetic field shields us from most of these. Very few of only the highest energy particles make it down to the surface. Those are a rarity. So it's for you and me down here on the Earth, it's not particularly dangerous. But for satellite operators, this is a particularly big concern. We know we know a couple of different mechanisms that can accelerate particles up to this energy. Interplanetary shocks. So transient things blow up on the sun and they start flying out and they drive a shock wave like a Concorde or a supersonic airplane in front of it. That can accelerate particles. Magnetic field lines can snap. We call it magnetic reconnection. It's like a slingshot that throws out particles that happen to be sitting on it. There are, again, a number of different ideas, but we do not have a good enough understanding so that we can when we see an event, we can predict, for example, will this be a particularly dangerous time period or not? So 3 questions Parker Solar Probe had to or will have to answer. Why is the solar wind accelerated? Why is the solar wind so hot in the corona? And where do these energetic particles come from? So let's look quickly about Parker Solar Probe itself. The concept is not new. In fact, in 1958, in the summer, NASA was funded. And in 1958, October, a panel was formed by the National Academy of Sciences, the so-called Simpson Committee, which was also co-chaired by Van Allen, the discoverer of the radiation belts. And the question was asked of this eminent committee, what should NASA do? Where should we go in the long term, in the future? So they had a number of brilliant ideas back then, including well, maybe we should go to the moon one day and make measurements from there, which we have done. Others said that, well, maybe we should go to the outer planets, which was back then an unthinkable idea. That, well, how do we get there? We have done that since 1958. And then they also had an idea, we should go near the sun inside the orbit of Mercury. Well, we have been trying ever since. NASA had 8 major science implementation studies where we said, all right, let's do this. And we said on, so how would you do it? And we either came up that, well, we just don't have the technology, or that it's way too expensive, and so nobody is going to pay for that. So not till 2008, when we finally converged on a design, and this is what you see in the lower right corner, the previous versions of the spacecraft above, but the actual, what we started to build was designed in 2008. It was approved by NASA. We started construction in 2010. It took 8 years to put the spacecraft together to be launched in 2018. So finally, we got to the launch pad on 2018 at August. Now to get to the sun, it was a tiny little bird for as far as NASA birds are concerned, but it required the biggest rocket we could find, which is a Delta IV Heavy. So I will come back to this. Why on earth did we use the biggest, most powerful rocket in the US arsenal to launch a tiny little bird into space? So we launched it in 2018. We already had 5 Venus encounters and a number of orbits. In each orbit, we get a little bit closer and a little bit closer to the sun. And now that we are getting to be in June of 2022, we are just starting our 12th orbit. That will take us still only to 13 solar radii. It will take a couple more years till 2024 when we will reach our final intended perihelion, closest approach of below 10 solar radii. So why on earth takes us so long to get too close to the sun? When I give talks to high school students, they laugh and they say that, well, that should be the easiest thing, just fall right in to the sun. I mean, the hard thing is how you get away from the sun, from the gravity well of the heliosphere. It should be really trivial to go near the sun. It turns out that not quite, because we are not starting from a standstill, but we are starting from the surface of the Earth, which is zooming around the sun at 30 kilometers per second. Well, that's why we don't have to worry about the Earth ever falling in to the sun. So the satellite taking off from Earth already has a 30 kilometer per second speed. In order to fall in, we need to slow down. So we took the biggest rocket and we launched this tiny little bird. And then we basically stepped on the brake as hard as we could to slow it down so that we could start falling in. And even with all the oomph of the Delta IV Heavy, we cannot get as close as we wanted. In theory, we could get just inside the orbit of Mercury, but we want to get much, much closer than that. So the solution was that we fly to Venus, and at Venus, we use a Venus gravity assist. Now, gravity assists in the past were used mostly at Jupiter to give extra speed to pioneers, the Voyagers, so that they could actually leave the gravity well of the sun. So typically, you go behind the planet, and the planet sort of pulls it along the spacecraft, speeding it up, giving it extra speed. Well, we did the exact opposite here with Venus. We went in front of Venus, and it was pulling us back in our orbit, slowing us down. Now, Venus, unfortunately, is nowhere, or fortunately or unfortunately, it's much smaller than Jupiter. So each encounter can only give us a little bit of reduction in speed. So we need to come back over and over again to Venus to get a little bit more kick and slow us down a little bit more, thus allowing us to fall into the sun. Now, it turns out it has advantages, because going near the sun is a very difficult technological thing. So rather than just going for broke at the right away, it allowed us to get closer and closer to the sun and see that our engineering solutions are indeed working. So let me show you just sort of quickly the timeline. Let's see if I can get my cursor back. I think this one. So what you see here is that we launched, we had a number of, all these green numbers are the Venus gravity assist, and then how close we get to the sun is listed on the bottom. So we are right now in 2022 in the middle, and so we are at 13.28 in solar radii. It will take a couple more years for us to get below 10. So the orange curve is just our distance from the sun as we orbit around. Now another curve here, the blue one, is the speed of the spacecraft. So sorry, exactly backwards. Orange is the speed of the spacecraft. So we are getting closer and closer to the sun when we are perihelion, as Kepler's laws dictate. We get faster and faster. So at the moment we are traveling, when we are close to the sun, over 160 kilometers per second. And we will climb up to over 190. This is by far the fastest moving human-made object ever. So remember, the biggest rockets, 10 kilometers per second, the speeding bullet below 1, Earth at 30, and now Parker's Solar Probe will go at 190 kilometers per second. This is comparable to the speed of the solar wind itself, except it's sideways, so perpendicular to the Sun-Earth line. All right, so here is the bird. It is not a very big one. It's from tip to end, it's only 3 meters, and only half of it, this golden part, is the spacecraft itself. The rest is the heat protection system, because as we get near the sun, it gets really hot. So at well over 1,000 degrees, so no electronics would survive. That was part of the technological issue that we couldn't overcome in previous decades. So it required this big heat shield in front of the spacecraft, which can withstand, not only withstand the heat, but that it steps down so that the backside of the heat shield needs to be cooler. It's not really helpful if it exactly radiates the same temperature as the front. So it is a carbon-carbon foam material, very light foamy stuff that actually rejects the heat out to the side. So very well, still hundreds of degrees come across, but a regular heat shield in the front is enough to bring the temperatures down here well into room temperature, what our electronics like to see. In fact, those instruments that are out in the breeze, in dark space, in the shadow of this heat shield, they actually get too cold. It doesn't matter that we are near the sun. The dark space is just as cold near the sun as here at 1 AU or at 100 AU. So we actually have to provide heat, electrical current, to keep the instruments warm enough. The next question was, well, how do you generate electricity when you are so close to the sun? And people usually point out that one thing we would have plenty of is light. So you should need just a small solar panel and you will generate just plenty of electricity. The problem is that solar panels don't function very well above 1,000 degrees. They tend to melt. And so we had too much too good. It's sort of like saying that I am very thirsty and then somebody points out there is the fire hydrant, open it. Yeah, it's water, but too much of it. So how did we solve this problem? So our solar panel that you see here, it actually, as we get closer to the sun, first of all, it bends backward so that most of it is actually in the shadow, so that only the tip of the solar panel sees only a crescent of the sun. So, and even then it was getting too hot. So we needed to do active cooling. We are actually piping a coolant on the backside. And then what you see, this skirt, the coolant is flowing around just like a car's radiator, and then it radiates the heat away, and then it circulates back to the solar panel. So the question was asked that, so what sort of NASA special coolant are we going to use? And so after much research and all sorts of exotic material and liquids, finally it came out that the best coolant there is pure water, pure H2O. It doesn't corrode the pipes. It actually has an excellent capacity to carry heat away. So that's all it is. It's plain water cooled, just like a water cooled engine in a car. So those are just two of the technical difficulties that we were able to overcome. In terms of measurements, so we have an instrument just one which actually looks directly into the sunlight, measuring the incoming solar wind. It's It's made out of niobium, which is a metal that doesn't melt till very high temperatures. And so are these electric field antennas. The rest of the instruments are nicely back in the shadow. So let me turn the spacecraft around where you can see the instruments much better. So there is an instrument here measuring the solar wind particles. This particular instrument and the one behind it down here, it measures the energetic particles. This one is a sideways looking camera. And then we have magnetometers measuring the magnetic field out on the boom. All right, next. So now that we covered what is the spacecraft, right, and what sort of instruments it has, so what are the discoveries that we made so far? And I have to remind you, we are not quite at our closest approach, but we already made some very surprising discoveries. So here I am showing you a number of measured properties. So first at the bottom panel, this is just the distance from the sun. This is our first orbit. So obviously when we were nearest the sun, then we were on at 35 or so 36 solar radii. And then both sides, it's a little bit more. The only other thing I want to draw your attention to is the upper panel where the green beagles are the measured total magnetic field, and the black are the radial component of that. Again, it's a vector, it has three components. It's just the radial component of that magnetic field. And so what is not surprising that the magnetic field kept rising as we got closer and closer to the sun. That we fully expected. You get closer to the source, you have a bigger magnetic field. But what surprised us is this hairiness in the radial component. Notice that so the magnetic field in the radial direction was actually somewhat pointed, so we call that negative in this particular plot. But quite regularly, it switches signs and becomes positive, then it comes back. It completely rotates around 180 degrees quite frequently. We called these switchbacks at the time and said, wow, this was completely unexpected, the solar wind magnetic field doing that. We expected that near the sun, everything is dominated by the solar wind and everything will be radial purely. Where would the energy come from to flip the magnetic field backwards? So here is a blow up. This is just a couple minutes of data. And now I draw your attention just to the second panel where the red curve shows the change in the magnetic field, the radial component. So here is one of these switchbacks. It goes to the opposite signs, wiggles around just for a few minutes, then comes back to the original value. Again, goes to the other side. There are several of these switchbacks. Now, notice also that the blue line, which is the velocity, also does a jump exactly at the same time as the magnetic field. So very, very well correlated with the magnetic field. That's called Alfvény condition when the two are correlated rather well. We've seen switchback type of observations near Earth before, but once or twice a year. I mean, here we have them every 10 or 20 minutes, and they are just non-stop. So what does this really mean? So here's an artist's depiction that we have all these beagles coming out from the sun, then relax by the time it gets to 1 AU. So this is some sort of hint as what's going on deeper in the sun, how the solar wind is accelerated. We have, again, a number of different ideas what this could mean. Are these off-in waves that steepen? They are magnetic reconnection, field lines snapping, or we have little jets that we never observed before on the sun shooting out and sort of coiling up the field lines. So yes, we've seen something we didn't expect. It must help us to answer the question of what happens near the sun. How is it the solar wind? How is it accelerated and heated? But so we have a piece of the puzzle. We are just not quite sure where to put that puzzle piece yet. Other piece of observation. So normally when we measure gases and we say what is the velocity, density, temperature of a gas, what we really mean is what is its bulk property. In room temperature, it's not that every oxygen and nitrogen molecule has the exact same temperature as every other one, there is a distribution, and it's typically a Gaussian distribution like this red curve, where if you plot their velocity and the number of the particles in that volume, the most of them will be at some sort of average value, and then if you go a little bit slower, a little bit faster, the number of them will drop. That's sort of what equilibrium looks like in a gas. Now, in space plasmas at 1 AU, curiously, we found that the same kind of distributions describe the gases there, which is curious because there are very few particles in the solar wind, typically 10 particles per cubic centimeter, which is better vacuum that vacuum chambers can generate. So these particles don't collide with each other, or very typically a solar wind particle coming from the sun has maybe 1 or 2 minor collisions before reaching Earth. So these are, you can't argue that these are collisionally relaxed distributions. Nevertheless, somehow the electromagnetic fields manage to distribute the energy between the particles so that it looks like an equilibrium distribution. So typically we have a hydrogen peak, that's the primary solar wind, and then we typically have the alpha particles or the ionized helium. They tend to travel a little bit faster than the protons, the stripped hydrogens. So we see them as a second peak. Now, what we started to observe with Parker's solar probe, that there is a second distribution that we needed to invoke in order to, the black curve is the data. And so in order to fit this data, we couldn't just fit a single Gaussian for the protons and the helium. They are actually jets that still coexist. Somehow the equilibrium has not reached its final state. It actually gets worse. So if in reality, what I plotted before, it's a one-dimensional simplification. In reality, when a particle moves, it can move left, right in three-dimensional space. So it can go faster, slower, it can go a little bit left, a little bit right. So I'm now showing here 2 dimensions, and I promise I'm not going to show it in 3. Again, but you can see the hydrogen, the protons stream at a certain speed, and the color or contours depict how many of these particles exist. So the peak of the distribution is at a certain velocity in a certain direction. And if you move away from this peak, it nicely drops off like a Gaussian distribution. And here you can see the alpha particles. Now, we do have an instrument that is actually smart enough that it eliminates the alpha particles because they have different charge to mass ratio. So we only look at the protons, and rather than getting this nice elliptical distribution, this is what we measured. And this is a long shot away. Yes, there is a hint for a core distribution, but if you look at what is this? Higher energy tail, that some of the particles got kicked up to a little bit higher energy, and then they seem to be diffusing along the magnetic field direction. We are still trying to wrap our heads around that. This is what we see at 1 AU. This is what we see near the sun. We see something, ongoing processes that we are still trying to wrap our heads around it. Now, one of the other objectives we had is try to reach below what we call the Alfvén point. As I mentioned earlier, the solar wind is kicked up to extremely high speeds. In fact, so fast that the waves traveling inside cannot match that speed. Sort of like as a supersonic airplane that going over the sound of speed, that when it's moving faster, no information can go ahead of it. So you don't hear, for example, a supersonic jet approaching you because the jet is faster than the sound can travel. And then it, of course, results in a shock wave in front of it. But the whole solar wind is moving at this supersonic, or we call it supermagnetosonic speed, because in a plasma, there are multiple types of waves, not just sound waves. And so typically at 1 AU, the speed of the solar wind is at least 10 times faster than the fastest moving electromagnetic wave. That means that if something is happening in the solar wind and the ripples spread out, even the ripples that propagate backwards in inertial frame, that all of them are moving away from the sun. No information can reach back to the sun, no matter what happens in the solar wind, because the medium is moving faster than information can propagate. Now, as we get closer to the sun and we are observing this acceleration, so we are moving to regions where the solar wind is slower, we reach the point where the wave speed matches that of the solar wind. So look at just this one panel here. The black wiggles are the measured speeds, and the blue is the local speed of the fastest moving waves. And so we reach where these gray regions are a couple, well, maybe an hour or so, where the waves are actually faster. So during these regions, waves were in communication back with the sun. Now, this is particularly exciting. Why? So here is an artist's depiction. If all the waves are moving outward, they cannot really move backwards. But if the waves can go both ways, those waves can interact with each other, get into resonance with each other, and possibly be the reason for heating and accelerating the particles. Now, what we've also found that this boundary is rather corrugated and variable. So 2 orbits ago, we did cross a few minutes into below the off-in region. But the last orbit, we didn't cross at all. So it's a good thing that we still have 4 solar radii closer to go to the sun, because our orbit is like this in this artist depiction, that we are just skimming at the very edge of this very critical surface, and we really need to get into this inner zone to really investigate how the solar wind is heated and accelerated. Just a few words about energetic particles. The sun really didn't cooperate with us very much so far. The sun was rather quiet so far. It's just waking up. What I'm plotting here in 2 orbits, in the inside is the low energy particles, lower energy particles, and the outside is the higher energy particles, where both the height and the color indicates the fluxes. And normally what you have is that if you have higher energy particles, you usually have associated lower energy particles like here. But what we found very curious, that we had time periods when we were near the sun, that we had high energy particles without, so for example, if you look at, so there are high energy particles more than low energy particles. This is very, very curious. How is it that the sun managed to produce only higher energy, not the easier to generate lower energy particles? So yet another puzzle piece that we are trying to understand. So finally, a couple of just sort of neat things, not really related to our primary objective. This is our camera looking sideways. So what these white lines are actually dust particles zooming by us and reflecting some light. Those that are curved are actually dust particles that manage to hit the spacecraft, and the debris, well, single atom debris flying away from the spacecraft, and yet again showing up as reflecting lights. Don't worry, they take usually 1 molecule at a time, so the spacecraft is not going to disintegrate. But what was curious is that as we were flying closer and closer, do you see this faint outline of a trail where the red dashed line sort of hopefully draws your attention to it? It turns out that it's exactly the orbit of the asteroid Phaethon, which is known to be an active asteroid, meaning that it's sort of shedding. Normally comets shed dust behind them, asteroids don't. This particular asteroid does, and for the first time we actually can see the trail of the asteroid debris as it evaporates off from its surface. This is again from the Whisper camera, long-term images. So what you see here is the Milky Way in the background, because it's normally we remove that from the images, but here it shows that yes, indeed it's there. You see overexposed the light from Mercury and Venus. There is Earth far away from us, but there is this faint outline, and that's not a solar wind, and it's exactly in the orbit of Venus. And it turns out that Venus collects dust from the evaporated comets, and it's the sort of going around in the orbit of Venus, forming a disk. This was not seen before. It's not surprising, planets tend to do that, but it has not been observed before. And finally, as we had to go around Venus, we actually turned on our camera, even though we are not really a planetary mission. And so we only take white light images, and sort of normally one doesn't take pictures in white light of Venus because, well, it's cloud covered and what you will see is a lot of clouds. But it turns out as we went behind, this is the night side of Venus, and it's so incredibly hot, the atmosphere, that we can see actually temperature variation in the light. And it's on the right side, this is an older mission, the Magellan, that took pictures of in radar and mapped the surface altitude of the planet. So these pink ones are the highlands. And notice how well they correlate with the darker spots, which it turns out that that's colder air or atmosphere. Not surprisingly, that above the highlands is not quite as hot the atmosphere as over the lowlands. That was just unexpected, that wow, we can sort of see features below the clouds with white light camera. So I leave now just again reminding you some of the first and exciting things. Parker Solar Probe, of course, is getting closer to the sun than any other mission, just to illustrate that how much closer. The previous one was the Helios missions, a German mission back in the 70s, which just got inside, just barely inside the orbit of Mercury. And so how much closer we get really hot on our thermal shield, we go really fast, and it took a really long time to get to this point. So thank you very much, and I am open for questions. If I still have anybody with me.
No.
Yes, we're here.
Yeah. Oh,
Any questions? We're up at our observatory. I do have one. What's the life expectancy of the probe?
So our prime mission is till the end of 2025. So we better survive till then because, well, we were designed to do so. At this point, we didn't have any major mishaps. So we typically try to have redundancies. So we carry extra fuel and back up this and back up that. We haven't had to exercise any of that. So at this point, we have fuel for decades of operation. So the issue will be that the environment is not exactly without its dangers. For example, these dust particles, some of them are big and they pose dangers to us. You saw that we are water cooled. All it takes is a well-aimed bigger dust particle puncturing a hole in the cooling system. Then the water will get out, and so much for cooling, and then so much for electricity generation, and that would be the end of the mission. Luckily, it didn't happen yet. It's a very low probability event, but the longer you fly, you can only defy probability so long.
And I guess that ties into what I was going to ask, because you had mentioned that there was this very fine disk of in the orbit of Venus.
That is.
And in addition, I've seen images of the sun, and there's a surprising number of comets that come around and then get absorbed, which means that there's a whole lot of dust being dumped in there. And I wonder two things. One, what you just said about the probability of it puncturing the orbiter, but the other is, how does that disk of sun affect the data that you're getting?
So it really impacts the white light observations. The number of dust particles, even if they were charged, and some of them, probably most of them are, they are so few that compared to the solar wind density, it's negligible. So for our plasma and magnetic field, electric field observations. For the white light observation, it is the F corona to remove it from our images, because there's so much dust that if you just take the imager data, which is just a 2K by 2K CCD camera, if you just in white light, if you take the picture, what you will see is very much like in a foggy day, you turn on the headlight of your car and you will just see this haze. That's all we see. So the F corona, the dust environment, has to be modeled, and they remove this. And so our data, what you see here, the streams in the, so for example, you see solar wind streams coming out. That's after that much bigger signal is removed. These are the small variations on top of the dust background. So it is very important. Now, an interesting thing that we are finding, it was postulated the sunlight, if you get closer to the sun, it of course is more energy, so dust particles might evaporate, or light pressure would push them out. So it has been postulated that near the sun, there should be a dust-free zone. All the dust sort of pushed out by the photons. So now it has been argued how close it is, maybe 5, maybe 10 solar radii. We started to, so from nearer observatories, since we, no matter what, we had to look through 1 AU-verse of dust, we cannot see if there is a small region of free without the dust. On the other hand, for us, as we are getting closer and closer to the sun, as we are looking at the amount of reflected light from the dust, it's not growing nearly as fast as we would expect. We are getting closer to the sun, so we see more and more light reflected from the dust, but it's not growing nearly as fast as a simple spherical model that a solid model would predict. So it's a strong indication that indeed, not so far below us, indeed there is a dust-free zone. That's just sort of a curious. I don't think we will get to that. We will not break through to the dust-free zone, but it is sort of interesting.
So this will be traveling through an entire solar cycle.
Yes.
Of what, 11 years or so?
Yes, because the dust environment really has to do with the photonic environment, not so much the magnetic environment. Yeah.
Thank you.
Well, thank you. That was wonderful.
Good. Glad you enjoyed it. Any other questions from anybody?
Could I ask Bruce Cutler here? This is all very interesting, a bit over my head, much of it, but the discussion of the propagation of waves and the, I guess, submagnetosonic waves
Yep.
was quite interesting, but I did not really understand basically the source of those waves. And I guess the idea is that they're basically, since they are traveling towards the sun, they're adding energy, and that's a possible explanation for the activity in the Coronasphere?
Yes. So the sun, as I showed you at the very beginning, is constantly shimmering. There's also the convection, so that the fields from deep within the sun come to the surface and then they churn down. And there is differential rotation. So the equatorial portion of the sun rotates at a different rate than a little bit higher and higher latitude. So since everything is magnetically connected, as you saw these arcs, you are constantly twisting all these arcs around. So the foot points are spinning, the big arcs are twisted around. So that's where the waves come from, that the sun itself is producing these waves. They're wiggling the bottom of the field lines, basically, as the field lines leave the surface of the sun, and we see this wiggling. Now, the reflected waves, they have to do with the interaction of the waves with the solar wind. So every time there's an interaction, you have waves propagating in both ways. I mean, in all directions. So the reflected waves are just signs of interaction that happens further out in the solar wind. It happens everywhere, except when it's in the super alphanic or super magnetosonic region, they cannot reach back to the sun. Below the alphane point, these interaction waves can propagate back all the way to the surface. So the question is, do we have mathematical models that indicate that if you have constructive interference between the forward and backwards propagating waves, that can energize particles? So we wanted to see that, but so far we have only a few hours of data, so we can't really conclude which model is precise or not. It's just the hint is there that hopefully at the next after the next Venus encounter, when we get even closer to the sun, we will be fully immersed in the subalphanic solar wind, and finally we start to rack up some data to conclude one thing or the other about these models. I don't know if that answers your question.
Oh, that does. Thank you so much. This has all been very interesting. Thank you.
All right.
Do we have other questions?
I think it's a wrap, John.
Okay.
No question, but thank you very much.
Yes, thank you for your time this evening.
Yes, thank you very much,
Sure.
Dr.
Glad to
Szabo.
do so.
Yes.
Thanks again.
All right. Have a good evening.